Many liquids are essential in our daily life. They may include water, beverages, dairy products, chemicals, acids and bases, or pharmaceutical products. The quality of these liquids is determined by their chemical and physical properties. To assess these properties, various principles of measurement are used. One of these principles is the measurement of dissolved oxygen in liquids. Oxygen penetrates liquids in different ways, for example via oxygen-producing plants, waves, or gas exchange with the atmosphere. At the water surface, oxygen molecules migrate from the atmosphere into water and vice versa. Once the oxygen is in the water, it distributes evenly to achieve a uniform distribution in space. The established measuring principles for the determination of oxygen concentration are the amperometric and optical measurements. Let's take a look at how the amperometric oxygen measuring principle works. In 1954, Leland C. Clark, an American biochemist, developed the so-called Clark electrode to measure the oxygen concentration in blood. This type of amperometric oxygen sensor can be used to measure the oxygen concentration in many different solutions. An amperometric sensor usually consists of a gold cathode, also called working electrode, and a silver anode, the counter electrode. A DC voltage is applied to both electrodes. The cathode and anode are located in a reaction chamber that is filled with an electrolyte. The reaction chamber is separated from the medium by a membrane. This porous membrane allows dissolved oxygen to diffuse into the sensor. When the sensor is immersed in a medium containing oxygen, the difference in the partial pressure of oxygen between the inner and the outer membrane walls leads to the diffusion of oxygen through the membrane. The diffused oxygen is reduced at the gold cathode in the reaction chamber, resulting in a current flow that is proportional to the amount of transformed oxygen. The current is processed by the transmitter and displayed as oxygen concentration, partial pressure, or percentage saturation. After a certain period of time, a silver bromide layer forms on the silver anode. This layer reduces the effective voltage and thus the oxygen flow, which can lead to measurement error. In applications with high temperatures during cleaning or sterilization, the silver bromide layer is regularly removed. At moderate temperatures, however, it remains permanent. That's why sensors with reference electrodes are used in these applications. The reference electrode compensates for the increasing silver bromide layer via an internal regulating circuit, considerably reducing the maintenance for the sensor. The amperometric measuring principle offers a linear measurement via the complete measuring range and is thus suitable for high and low partial oxygen pressures and concentrations down to trace level. The optical oxygen sensor uses the fluorescence quenching measuring principle. This sensor is equipped with an LED, a photodiode, and a separating section that is covered by an oxygen permeable layer. In this layer, there are as many oxygen molecules as in the medium. This means the partial oxygen pressure in the layer is equal to the pressure in the medium. The layer contains marker molecules that are excited by an orange light and respond with a dark red fluorescence light. Oxygen molecules attach to the marker molecules and attenuate the fluorescence light, which is called quenching. The light signal is detected by the photodiode, processed in the transmitter, and displayed in the required units. In applications that involve higher temperatures, for example during sterilization or cleaning, sensors with reference LEDs are used. This LED compensates for the aging of the measurement LED and delivers reliable results even in demanding applications. The advantage of optical oxygen measurement is fast availability of stable measured values and extremely low maintenance. Amperometric and optical oxygen measurement is essential for quality assurance and process control in many industries, such as water and wastewater, food and beverage, life sciences, chemical and power industry.